Welcome to Brain Vision.
This is Chapter 6, Section 1, Problem number 11. We have a carton on an inclined plane, and it is being pulled up by a rope. So this is our inclined plane. It is at a 30-degree angle, and it's being pulled up by a rope. So let's call this force F sub R. And let's show the other forces acting on this carton. So the gravitational force is pointing down, as you all know. And then the normal force is going up, F sub n. So this is the free body diagram. So we're showing all the forces acting on the carton. So one thing that is given to us in the problem is also that this F sub r is causing a displacement. The direction of the displacement is actually up the inclined plane. So let's note it. Let's use the letter S to refer to the displacement vector. If the initial position is something like this, then the final position of the carton would be up there, so that this is the direction of the displacement vector. It's determining the direction of the displacement vector is crucial in order to calculate the work, because the general formula, let's remember, work equals to the force dot product the displacement vector. When we open this up, it's going to be F magnitude of the force, magnitude of the displacement vector, and the cosine of the angle between these two vectors, F and S. So since we're asked in all the parts of this problem, we're asked to calculate the work done. Basically, this is figuring out what theta is going to be really important for us. So in part A, we are to calculate the work done by the rope. So then if we're calculating the work done by the rope, what we have is the force exerted by the rope times the magnitude of the displacement vector and the cosine of the angle between these two vectors. So if we go back and look at a free body diagram, the direction of the displacement vector is up the inclination, and so is the direction of the force exerted by the rope. So then, as you can see, they're parallel with respect to each other, which means the angle between these two vectors is actually 0. So then cosine 0 would give us 1. Then when we're calculating the work done by the rope, all we need to do is actually plug in the magnitude of the force exerted by the rope, which is given to us as 72 newtons in the problem. So 72 newtons times the magnitude of the displacement, 5.2 meters. And the cosine 0, which is 1. So that equals to 374.4 joules. Now in part B, we are asked to calculate the work done by gravity. Then that's going to be equal to the magnitude of the gravitational force times the displacement, magnitude of the displacement vector times the cosine of the angle between F sub G and S. So going back to the free body diagram, this is the direction of the gravitational force. And if we carry the displacement vector here, we can see the angle between these two vectors, F sub G and S, is 90 plus 30 degrees. So theta here is 90 plus 30, which is 120. Then F sub G, the magnitude is given to us as 128 newtons. The magnitude of the displacement vector is 5.2. And then we have cosine 120 degrees. So if we do a calculation correctly, what we get is something negative due to cosine 120 being negative. So 332.8 8 joules would be the work done by gravity. So in part C, we are to calculate the work done by the normal force. Again, the normal force times the magnitude of the displacement vector times the cosine of the angle between these two vectors. If we look at the free body diagram, this is the normal force, and this is the direction of the displacement vector. As you can see, there is a 90-degree angle between these two vectors. So our theta is 90 degrees here. Cosine 90, as you all know, gives you 0, which then makes the work done by the normal force 0. This is a very well-known result, right? Because when the force is perpendicular to the displacement vector, and the angle between these two vectors is going to be 90, so the cosine 90 is going to give you 0. So work done is going to be equal to 0 for any force that is perpendicular to the displacement. Now, let's go to a new slide. So in part D, the question is basically is to calculate the net work done on this carton. Net work done on this carton is going to be equal to the summation of all the work done by different forces. So basically, we're going to use our answers to part A, B, and C, combine them in this part. So the first work we calculated was the work done by the rope, and then the second one was the work due to gravity, and the last one was work due to normal force, which was 0 anyways, but let's just put it there to have the complete understanding. So the work done by the rope was calculated to be 374.4 joules. And then we calculated the work done by gravitation to be something negative. It was 332.8 joules plus 0, right? So then the final answer would be 41.6 joules, the net work done. Now in part E, what we have is that now the force exerted by the rope, the angle of that force is different now. It is given to us as 50 degrees with respect to horizontal. So remember, the inclined plane is at 30 degrees with respect to horizontal. And now the force applied by the rope is actually at a 50-degree angle with respect to the horizontal, not with respect to the surface of the inclined plane. So the dotted line would be the line that is parallel to the surface of the inclined plane. Now we have 50-degree angle at which F sub r is being applied to. So this angle then would be 50 minus 30 degrees, which is 20 degrees. So then when we're calculating the work done by that new force, again, the formula does not change, of course. F sub r times s, the magnitude of the displacement vector, and times the cosine of the angle between these two now. Still, the direction of F sub s is not changed, right? It's the same. It's up the inclined plane. Let me draw it better, like this, right? This is the direction of s, but now the direction of F sub r is at a 20-degree angle with respect to s, so then we're gonna plug it in here. The magnitude of F sub r is still 72 newtons. The magnitude of the displacement vector is still 5.2. And now we have cosine 20 degrees. When we do the calculation, it will give us 351.8 joules.